So welcome back. So what I wanted to tell you is a bit what happens behind the scenes in PostgreSQL, right? Because you know the relational table from the comfort of your notebook. So what you need to know is that behind the scene, there is a machine with hardware. The machine has CPU, has memory, has disk, has tape. Even tape actually still exists today. Your files at ETH are backed up on tape. It takes hours to retrieve them if you want the backup, but they have little robots that manage them. And it's good to know that some of them are volatile in the sense that if you shut down the electricity, it's gone, but not a disk or a tape. A disk or a tape, if you shut down your computer and switch it back on, then that's fine, it's still there, right? So it matters for the D of ACID. But what's important to know here is that those at the bottom that are durable, they take more time to access as opposed to, for example, what is stored right on the CPU of your machine is going to be super fast, like nanoseconds, memory, a few hundreds of nanoseconds, disk maybe milliseconds, and hours for tapes. And there is also a correlation with the size, that when it's fast to access, you cannot put so much data, and the slow access, you can put a lot of data. So there is this correlation here. And by the way, the ones at the top are super expensive. The price of 1 byte is extremely expensive, but on a tape, that's totally inexpensive, right? So this is the idea. So technically, the data in a database is going to be in there, right? On disk, this is everything you want to persist, your relational tables, your indices, and so on. And in memory, this is what you have on the fly. When you execute your queries and produce tables, they will be in the memory. Okay. Now, you know, because of data independence, we're isolated from the details on disk, right? It looks like magic. You open your notebook, you say, create blah, 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 insert blah, 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 select blah, blah, blah. It just works. So it's like the magic happens in the notebook. As you might imagine, this is all stored on the disk of your machine when you insert data. And you know that the only way we can store things on a disk is as directories and files. Right? So these days with smartphones, we kind of forget about them, but if you have a laptop, you still see the directories and files. So PostgreSQL is going to store all of that as directories and files, but they are hidden from you, and you don't even need to bother about them. This is hidden. It's hidden, but if you look, you will find them. And actually, you can try to find them, but they are there somewhere. And if you do find them, this is what it will look like. Plenty of PG_ files, PG for Postgres, and this is your data. But of course, to a human, it makes absolutely no sense, right? This is just a proprietary format that basically stores the data. You should not actually access it directly. You should be using the PostgreSQL access to it. But nevertheless, it is here. And all the engineers of PostgreSQL worked very hard in order to manipulate the data stored like this. So the way it works is that you have the records here that you see in your Jupyter notebook, and they are going to be stored on disk in a specific order, like attribute by attribute, like this, with some additional data. You don't need to worry too much about that, but you basically see that the only way you can write on disk is a sequence of bits. It's a sequence of zeros and ones. So when you store your records, you have to put it in a specific order. Comes back a little bit on the question you asked before. So we have here the name, the address, the gender, and the birth date. Even though the order doesn't matter logically, on disk, there is one. So you do store the name here, and then the address, and then the gender, and so on and so on, right? Now it optimizes a little bit. So you could technically put it in that order. What it does in reality is that it's going to first store the ones that have a fixed size, like a specific number of 32 bits, a date, and so on. But everything that is elastic, like the name of a person or the address of a person, they will put at the end. And that makes it much easier to actually very quickly access the ones that have a known and fixed size, and a bit slower to access those that are a bit elastic, right? But it makes it tough because then the size is not always the same for all the records, right? PostgreSQL also have a magic way to store huge strings and huge binary numbers called toast. And it's literally slicing the strings like this and putting them in slices in yet another table. Now it's beautiful because this is actually a relational table, but it's hidden from you. This is a relational table that is used internally to slice all the huge strings and the huge binary data that you might have in your table. It's called toast. I think they have a very good sense of humor because, again, the slice of strings. And now I see that it's It's already 12, so I have to let you go. I just have 6 more slides. Next week, we'll celebrate. I'm going to give you an outlook on big data. We're going to be doing a quiz game, you know, testing your knowledge and so on, but there will not be any new material behind the 6 more slides here. Right? So I hope to see all of you next week for the quiz. I hope the TAs also can come because they'll compete against you. So you can try to beat the TAs if you work a little bit on the material. Thank you very much, everybody. Thank you for being here. Thank you, everybody on Zoom. And I will see you next week for the final celebration of the semester. Thank you.